Hello everyone, welcome to this lecture. Just a quick recap, in the last lecture we concluded our discussion on public key cryptography. So, in this lecture the roadmap is as follows. We will basically discuss some of the main results related to number theory which we have used during our extensive discussion on public key cryptography. I stress that we will not be having a full fledged discussion on number theory, because I personally feel that in a course on foundations of cryptography, we should basically just use the important facts from number theory, but I thought that probably we should have a very high level discussion on some of the important results which we used extensively during our discussion on public key cryptography. So, motivated by that, we will have this today's lecture based on completely on number theory, where we will discuss about modular arithmetic, prime numbers and their properties, and we will see the extended Euclid's GCD algorithm. So, let us start with modular arithmetic. So, imagine you are given two numbers or two integers a and big N belonging to the set of integers z, and here n is your modulus, where n is greater than 1. Then a mod n is defined to be the remainder r, such that the remainder r is in the range 0 to n minus 1, such that the relationship a is equal to q times n plus r holds for some integer q. If that is the case, then we say that a modulo n is r. So, for instance, if I want to find out 5 modulo 4, then 5 modulo 4 is 1, because if I divide 5 by 4, I get the remainder 1. In the same way, if I want to find out minus 11 modulo 3, then minus 11 modulo 3 is 1, because 1 is in the range 0 to 2, and minus 11 can be related to 3 by this relationship. Namely, I can say that minus 11 is 3 times minus 4 plus 1. It turns out that I can write minus 11 as a linear combination of my modulus 3 in another form as well. Namely, I can say that minus 11 is equal to 3 times minus 3 minus 2, and hence one might feel that minus 11 modulo 3 should be minus 2, but that is not the case, because as per our definition the remainder r should be in the range 0 to n minus 1. That is why minus 11 modulo 3 is 1, not minus 2. Now, we have the definition of a modulo n. So, if we have two integers a and b such that both a as well as b gives you the same remainder modulo the modulus n, then we say that a is congruent to b, and we use the notation that a and with this special equality symbol b modulo n. So, this means that a and b are equivalent in the sense that they gives you the same remainder when you divide them by the modulus n. So, as per the definition of a modulo n, it turns out that if a is congruent to b modulo n, then this is possible if and only if the difference of a and b is completely divisible by n, because if a gives the remainder r modulo n, and since a is congruent to b modulo n, that means b modulo n is also the same remainder r, and if I subtract b from a, then the remainder r and r cancels out, and what I obtain is that a minus b is completely a multiple of n, and hence it will be completely divisible by n. So, we have some well known arithmetic rules for modular arithmetic. So, for instance, if we have two numbers a and b, and if I know that a modulo n is a prime and b modulo n is b prime, then I can say that a plus b modulo n will be the same value as you obtain by doing the operation a prime plus b prime modulo n. The same is true for subtraction as well as multiplication. So, the way you can interpret these rules is that you can imagine as if you can first perform the modulus, or you can first do the reduction modulo the modulus n, and then you can perform the addition, subtraction, multiplication operation instead of adding or subtracting or multiplying and then doing the reduction modulo n. To be more specific, for instance, imagine I want to compute the value of this number, namely I want to perform the product of 10933028 and 190301 modulo 100. If I want to compute this value, then there are two ways to do that. The first way will be that I first perform the product here, or I first compute the product here, and then I do the reduction modulo 100. But this will be a complicated operation, because multiplying these two large numbers will be really challenging. I can't do it easily on a notebook. On the other hand, the same operation I can perform by first reducing the individual values here, namely 10933028 and 190301 modulo 100, and reducing each of them modulo 100 is very simple, because I just have to focus on the last 2 digits here, which I get as 28 and 1, and then I can multiply 28 and 1 and then again reduce the answer modulo 100, and whatever I obtain by option 1 and whatever result I obtain by option 2, they will be same as per the above rules of arithmetic, rules of modular arithmetic. So, this is a very powerful trick or powerful concept applicable in the context of modular arithmetic, where where instead of applying the operation and then doing the modulo or reduction modulo n, you can first reduce the operands modulo n and then you can perform the operation, and if required you can again perform a reduction modulo n. So, we have seen the addition, subtraction and multiplication modulo n. What about modular division? So, the question is, can we say the following: imagine a modulo n is a prime and b modulo n is b prime, then can we say that a divided by b modulo n will be the same as a prime divided by b prime modulo n? The answer is no, because in fact it turns out that the operation a divided by b modulo n is not at all well defined. So, to demonstrate my point, imagine my a and b are 3 and 5 and my modulus is 4. So, I am given 3 modulo 4 is 3 and 5 modulo 4 is 1, and I know that 3 divided by 1 modulo 4 would have given me 3, but if I want to calculate 3 divided by 5 modulo 4, I do not have the answer, because this operation 3 divided by 5 modulo 4 is not at all well defined. That means, in modular arithmetic I cannot say that if I am given that the product of AC modulo n and the product BC modulo n are same, then I can't say that cancel out C from both the sides and I cannot get the implication that A modulo n is equal to B modulo n, which would have been possible if I have performed the same operation in regular arithmetic and C would not, and C is non-zero. That means, in the regular arithmetic, if I know that AC is equal to BC and C is not 0, then I can say that if I divide both the sides by C, then I obtain A is equal to B. But the same thing I cannot conclude in the modular arithmetic, because modular division is not well defined. So, now let us discuss some of the algorithms for modular arithmetic. So, imagine we are given 2 operands A and B, each of size little n bit, and a modulus big N whose size is also little n bits, and some of the common operations which we encounter in public key cryptography are to perform the modular addition, multiplication, subtraction and the exponentiation. So, remember, modular exponentiation is a very important operation in almost every instantiation of public key crypto system. We encountered modular exponentiation. So, we now want to have algorithms to perform this modular arithmetic operations, such that the resultant algorithms, their complexity, their time complexity should be some polynomial function in the number of bits, namely little n. So, it turns out that if I want to perform modular addition, subtraction and multiplication, I can perform them in poly of little n number of bit operations. But what about modular exponentiation? Imagine I want to compute a to the power b modulo n. A naive algorithm will be that I perform a square modulo n, whatever is the result I multiply it again with a and do a modulo n, and like that I have to perform basically b minus 1 modular multiplications. And since each modular multiplication requires a poly of n number of operations and I am performing b such order of b such operations, one may say that the overall time complexity of this naive modular exponentiation algorithm will be O of b times poly of n bit operations, and hence its overall polynomial. But that is not correct, because what exactly is the value of little b here? I have to express the value of little b also as some function of little n, and it turns out that the magnitude of little b here is some exponential function in the number of bits little n. Basically, b can be as large as 2 to the power n. That means, this naive modular exponentiation algorithm, its time complexity is exponential function in the number of bits that you need to represent your a, b and the modulus, and that is why it is an exponential time algorithm. We cannot use this naive exponentiation algorithm to perform to compute a to the power b modulo n. So, now what we are going to discuss is we will see a polytime algorithm to compute modular exponentiations. So, this method is called as the square and multiply method, And to demonstrate the algorithm, I will take an example here. I want to compute a to the power 53 modulo n. Remember, the naive approach will be to multiply a 52 times, and with each multiplication you do a mod n operation. So, basically the naive approach will require you to perform 52 modular multiplications, but what we are going to see here is that using the square and multiply method we can perform the same computation with just 9 modular multiplications. So, the idea behind the square and multiply method is as follows. So, I express my exponent 53 in this case in binary, and depending upon the bit representation of 53, wherever I have the bit value 1, I have to take that power of 2, wherever the bit value is 0, I have to exclude that power of 2, and hence I can say that 53 depending upon its binary representation can be expressed as summation of these powers of 2, and hence I can say that a to the power 53 is nothing but the product of some selective powers of a, namely a to the power 32, a to the power 16, a to the power 4 and a to the power 1. So, the idea behind the square and multiply method, as the name suggests, is that in each iteration we will accumulate or we will compute the successive powers of a. That means, we will start with a power 1 and then we will go to a square, then from a square we will go to a to the power 4, then from a to the power 4 we will go to a to the power 8 and so on, and then selectively depending upon the current bit in the binary representation of the exponent, namely 53 in this case, we will decide whether to accumulate the current power of a or not, and that is why the name square and multiply. In a more detail, imagine I write 53 in this binary representation from LSB to MSB in this form, and as I go from LSB to MSB, the different powers of a that I obtain as I go from one current bit to the next bit is just a square of the previous power, right. And it is easy to see that my goal is to compute a to the power 53, and a to the power 53 basically can be computed by just multiplying some selective powers of a, namely the powers of a corresponding to the bit positions where in the binary representation of 53 I have the bit 1. So, based on this idea, the algorithm is as follows. So, we set an accumulator here which will have the final answer. The final answer that I want to compute is a to the power b or a to the power 53 in this case. So, I initialize my accumulator to be 1, and once I perform then all the iterations, my accumulator will have the final answer. So, in each iteration what I am going to do is I am going to do a conditional update, namely I will do the operation that y is equal to y into current power of a depending upon whether my current bit in the exponent b which I am exploring right now is 1 or not. So, for instance, the current I start with the LSB of 53 or the exponent b, right now the bit is 1, that means I have to accumulate this power, and that is why I will update my accumulator to by existing y and the current power of a, and then I go to the next power of a and I check the bit position is 0, bit is 0. So, I do not need to accumulate this power. Then I go to the next power of a which will be a to the power 4, and I check the current bit, it is 1, that means I have to accumulate this power. So, that is why I will update my accumulator by multiplying the current content of the accumulator with the current power of a. Then I go to the next power of a which I do not need to include or accumulate because the bit position in the exponent is 0. Then I go to the next power of a and I check the bit position of the exponent in its binary representation, it is 1. So, I have to accumulate, and hence I update my accumulator, and then I finally go to the MSB of the bit representation of my exponent, it is 1, that means I have to accumulate the current power of a, and hence that is my final answer. So, I am not writing the exact pseudocode here, you can understand the pseudo, I hope you will be able to write down the pseudocode here, but the idea here is that I will need to perform a sequence of iteration, and the number of iterations is nothing but the number of bits that you need to represent your exponent b, and in each iteration we have to do a compulsory squaring to compute the next power of a, and an optional accumulation depending upon whether the current bit in the binary representation of the exponent b is 0 or 1. And it turns out that in the worst case my exponent b could be such that all the bits in its binary representation is 1. That means, in the worst case in each iteration this optional accumulation has to be performed compulsorily. But even in that case the total number of modular multiplications that we end up performing is 2 times n, which is some polynomial function in the number of bits that you need to represent your n, and your modulus and your numbers a and b, and hence this is a polytime algorithm, and this is the algorithm which we use to perform modular exponentiations in all our public key crypto systems. Now, let us discuss about prime numbers. So, the definition of prime numbers is that an integer p greater than 1 is called a prime number if its only positive factors are the number itself and 1. And a number positive integer greater than 1 which is not prime is called as composite number. And a well-known theorem of arithmetic, which is also often called as the fundamental theorem of arithmetic, is that any number n greater than equal to 1 can always be expressed as product of different powers of prime, and this is true for every n greater than equal to 1. This is a well known fact which we can prove using induction. I am not going into the exact proof, and there is another well known fact from number theory which says that there are infinitely many primes. It is not the case that you have only finite number of primes, and again this theorem we can prove using contradiction or any other proof method. So, there are several well known proofs to prove the fact that there are infinitely many primes. I am not going into the details of the proof here. So, if you recall that in our RSA crypto system and also in the context of Al-Jamal encryption scheme, we basically require as a part of the setup description of a prime number to be available to all the parties, and the prime number should be sufficiently large. So, the question is how exactly we pick the prime numbers. That means, we need an algorithm to check whether a randomly chosen n bit number is a prime number or not, and there is a naive algorithm for doing that, and the naive algorithm is based on the fact that if a number p is composite, then it has at least one of the divisors which is less than or equal to root p. And the proof of this theorem is very simple, because if you have all the divisors of a composite number p greater than root p, say you have two such factors a and b, and neither a and nor b is less than equal to root p, and both a and b are the factors of p, and if p is composite, then it turns out that the product a b will be greater than p, which is a contradiction. So, that means if at all you have a composite number p, it is bound to have at least one of the factors in the range 2 to root p or 1 to root p. And based on this observation, we can have this following primality testing algorithm. So, imagine you are given a number p and you want to verify whether the number p is prime or not, and say the number p is an n bit number. So, the naive algorithm is basically you check whether there exists any divisor I in the range 2 to root p for the number p. Okay. Because if indeed p would have been composite, it is bound to have at least one of the divisors in the range 2 to root p. That means, it will have at least one divisor I in the range 2 to root p, and that is what you are searching in this naive algorithm. It turns out that the running time of this algorithm is order of root p divisions, because you are performing root p number of divisions in this algorithm, and since p is an n bit number, the magnitude of p is 2 to the power n. So, basically you are performing 2 to the power n by 2 divisions in this naive algorithm, and hence this is an exponential time algorithm which we can't use in practice to test whether a given number p is prime or not if my n is sufficiently large. So, it was really a very challenging problem to verify whether a given number p is prime or not in polynomial amount of time. In fact, people believe that it is not possible to come up with a polytime algorithm to check whether a given number p is prime or not, but history was made in year 2002 where a group of computer scientists from IIT Kanpur, namely Maninder Agarwal, Neeraj Kayal and Nitin Saxena, they came up with a polytime algorithm, polynomial in the number of bits that you need to represent your prime p number p, and they came up with this polytime algorithm which tells you whether a given number p is prime or not, and that algorithm is now well known as an AKS algorithm. So, you can use that algorithm to check whether a given number p is prime or not, but it turns out that we do not use the AKS algorithm, because even though it is a polytime algorithm, the underlying polynomials are sufficiently large, and that prevents us from deploying this algorithm as it is in practice. So, instead what we do in reality to check whether a given number is prime or not is what we use an algorithm which is called as Miller-Rabin primality testing algorithm, and it is a randomized algorithm in the sense that you cannot always trust the output of this algorithm, in the sense that for 99.99% cases it will give you the right answer, whereas there is a small error probability in the output of this algorithm. That means, even though your input may not be a prime number, it may end up labeling the number as a prime number. So, in that sense it is an error prone algorithm, and the reason we use this Miller-Rabin test to check whether a given number is prime or not is that its running time is super fast compared to your AKS algorithm. I stress that the AKS algorithm is completely error free. You can completely trust the outcome of the algorithm of that is given by the AKS algorithm, because it is a deterministic algorithm. There is no randomization involved as part of the algorithm. Now, let us discuss about greatest common divisor, or GCD. So, if A and B are two non-zero integers, then the GCD of A and B is the greatest integer, which is a common factor for both A as well as B. And if we have two numbers or two integers A and B whose GCD is 1, then we say that the integers A and B are co-prime. And if we have such several pairs of such numbers or several integers, say A1 to An, such that pairwise they are we say that they are pairwise co-prime or relatively prime if pairwise the GCDs are GCD is 1 for every pair of integers ai comma aj in the list. So, if we want to find out the GCD of two numbers A and B, then the Naïve algorithm will be that I first find out the prime factorization of A, because as per the fundamental theorem of arithmetic, I can express A as the product of powers of prime, and in the same way I can express my number B as the product of powers of prime, and then I can say that the GCD of A and B is nothing but I take the minimum exponents from individual prime factorizations of A and B and arrange them, and that will give me the GCD of A and B. But the problem with this algorithm is that how at the first place I find the prime factorization of A and B. So, it turns out that we can do something very interesting here. We can use an efficient algorithm to compute GCD algorithm, and this algorithm is called as Euclid's GCD algorithm. And the base for Euclid's GCD algorithm is the following fact. So, if you are given integers A and B such that A is B times Q plus R, and if your goal is to find GCD of A and B, then GCD of A and B is nothing but GCD of B and R if A is equal to B times Q plus R. Again, I am not giving the proof of this fact, you have to believe me, but based on this we can find out an algorithm to compute the GCD of A and B. And basically what we do in this algorithm is we set my x value to A and y value to B, and iteratively I find the value of x modulo y. I set my current y to be the next x, and I take the remainder of my current x modulo y to be the next y, and I perform this operation till my y becomes 0. As soon as my y becomes 0, which will eventually happen, I obtain the x at that point to be the GCD of A and B. And the correctness of this algorithm follows from the fact that GCD of A and B will be same as GCD of B and R, and GCD of B and R will be same as GCD of R and B modulo R, and so on. That means at every step I am basically reducing the value of so called B, and eventually it will become 0. So, if you are wondering that what is the time complexity or how many modular divisions I am performing here, or how many mod operations I am performing inside this Euclid's algorithm, I can come up with a exact bound using what well known Lem's theorem, which says that if the GCD of A comma B is computed using Euclid's algorithm and it needs n number of divisions, then your B should be at least the n plus 1th Fibonacci numbers, namely B should be greater than or equal to f of n plus 1. So, here f of n plus 1 denotes your Fibonacci n plus 1th Fibonacci number. If you are wondering what is the Fibonacci number, it is a sequence starting with 0, the next number is 1, these are the first two Fibonacci numbers, and then if I want to compute the value of the ith Fibonacci number, the ith Fibonacci number is basically the summation of the previous Fibonacci number and the previous to previous Fibonacci number. So, that is my Fibonacci sequence here. So, what Lem's theorem basically says is that if the Euclid's GCD algorithm would have performed n number of divisions, then the magnitude of B will be at least as large as the n plus 1th Fibonacci number, and There also exists well known lower bounds on the value of the nth Fibonacci number. It says the lower bound says that for every n the value of the nth Fibonacci number is at least alpha times n minus 2, where alpha is also called as the golden ratio, namely 1 plus root 5 over 2. So, based on these two facts, I can say that if my GCD of a comma b needs n number of divisions, then it's at most the n will be at most 5 times log of b to the base 10. Hence, asymptotically the number of divisions that we need to perform in this algorithm is proportional to the number of bits that we need to represent the value b, and hence the overall algorithm is an efficient algorithm. It turns out that we can use the Euclid's GCD algorithm to do something more. So, to understand that, let me first quote here Bezout's theorem here. So, what Bezout's theorem says is that you can always express the GCD of two numbers a and b as the linear combination of the numbers a and b. That means, you can always find out linear combiners s and t such that you can express the inputs a and b as a linear combination which will give you the GCD of a and b. That means, the GCD of a and b can be always expressed as a linear combination of the inputs a and b, where the combiners s and t always exist. And if you are wondering how exactly you can find out this Bezout's coefficients s and t or the combiners s and t, well, you can do that by performing some extra bookkeeping or maintaining some extra variables in the Euclid's algorithm. And this extended algorithm where you perform the extra bookkeeping activity to find out the linear combiners s and t is also known as the extended Euclid's algorithm. So, I will not go into the full details of how exactly this extra bookkeeping happens in the Euclid's algorithm. Let me demonstrate it. So, suppose you want to find out the linear combiners or Bezout's coefficients for the numbers a to be 252 and b to be 198. So, if you see the way the GCD algorithm will operate, the Euclid's GCD algorithm will operate for the input a to be 252 and b to be 198 is as follows. In the first iteration, your a will be 252, b will be 198, and you will obtain the value of 252 modulo 198. In the next iteration, your a will become 198 and your b will become the current remainder 54, and so on, and you do this operation till your remainder becomes 0, and when your remainder becomes 0, you know that 18 is your GCD. So, now your goal is to find out the linear combiners, so that you can represent the GCD 18 as the linear combination of 252 and 198, and for that what we can do is we can backtrack here, and we can see that I can rewrite 18 to be based on this equation, I can rewrite as 18 to be 54 times 1 minus 36, and if I go back one step above, then I know that my 36 is nothing but 198 minus 3 times 54. So, if I come back here and I substitute the value of 36 here, then I obtain that 18 can be rewritten as a linear combination of 54 and 198, but that is not my goal. And what I can do is, again I can go back one step up and I can rewrite and my 54 as a linear combination of 252 and 198, and if I substitute that linear combination in this last equation, I end up getting that 18 is represented as a linear combination of 252 and 198. That means, my Bezout's coefficients are 4 and minus 5. So, in this demonstration, actually to find out the Bezout's coefficient, I did a backtracking, but in the actual extended Euclid algorithm you need only the forward pass, you do not need to do a backtracking to do the bookkeeping and find out the Bezout's coefficient. So, how exactly this extended Euclid's GCD algorithm will be useful? So, it will be useful to compute multiplicative inverse modulo n. So, recall how did the way we defined the multiplicative modulo n operation. So, a into b modulo n is defined to be the remainder of a and b, a into b modulo n, and recall that we define an integer b to be the multiplicative inverse of a modulo n if the product of a and b modulo n gives you 1, and we use the notation b is equal to a inverse to denote the multiplicative inverse of a modulo n. And the basic fact here is that if b is the multiplicative inverse of a modulo n, then a is also the multiplicative inverse of b modulo n. And it turns out that if indeed we have one multiplicative inverse of A modulo n, namely if we have a B such that A times B modulo n is 1, then so is B plus any multiple of the modulus n. That means, it does not matter whether you add multiples of modulus n to B or you subtract multiples of modulus n from B, all of them also will be the multiplicative inverse of A modulo n. And this is because of the fact that A times B plus minus k times n ends up finally giving you A B modulo n, and since B is multiplicative inverse of A modulo n, A times B modulo n is nothing but 1. That means, if at all if multiplicative inverse exists, then they are infinite in number. Now, the question is, when exactly can we say that multiplicative inverse of a number A modulo n exists. So, there is a well known result in number theory which says that if you are given a modulus big N and an integer A, then the multiplicative inverse of A modulo n exists if and only if A is co-prime to n, namely if the GCD of A and n is 1. And we can prove the sufficiency part of this theorem. I will not go into the necessary proof of the necessity of this condition here. I will prove that indeed it suffices if A is co-prime to n to find out the multiplicative inverse of A modulo n, and that can be computed using Buse's theorem. So, imagine A is relatively prime to n, that means GCD of A and n is 1. That means, since the GCD of A and n is 1, that means if I run the extended Euclid's algorithm, I can find out Buse's coefficients, namely the linear combiners S and T, such that the GCD of A and n, namely 1, can be expressed as the linear combination of A and n using the combiners S and T. And now, if I take mod n on both the sides of this equation, and then on the right hand side I obtain 1 modulo n, and 1 modulo n will give me 1. But my left hand side, namely A times S plus n times t modulo n, will give me A times S modulo n, because n times t modulo n will give me 0, because it is a multiple of n. So, what I obtain if I by taking mod n on both the sides is that I obtain that relationship that A times S modulo n is equal to 1, which shows that S is actually the multiplicative inverse of A modulo n, and that is how you can obtain the or you can compute the multiplicative inverse of a number A if it is co-prime to n. So, that brings me to the end of this lecture. Just to summarize, in this lecture we just discussed on a very high level some of the basic some of the important facts from number theory, which we used extensively during our discussion on public key cryptography. Specifically, we discussed about modular arithmetic. We saw a polytime algorithm to compute modular exponentiations, which is a key operation which we perform in any public key crypto system or any encryption algorithm in the public key crypto system. We also discussed about primality testing, the properties of prime number, and we also discussed about extended GCD, extended Euclid's algorithm to compute the GCD of two numbers and to compute Buse's coefficient will be really useful to compute multiplicative inverse of numbers. Thank you.